When you write a Flutter widget, a simple container, a text, a column, Flutter takes that widget and eventually turns it into actual pixels on the screen. But how? What is the invisible engine that decides how big something is, where it goes, and how it looks? That engine has a name. It's called RenderObject. In this video, we're going to completely understand what a RenderObject is, what it does, why it exists, and how it works under the hood. By the end, you'll see Flutter in a whole new way. Let's go. Before we talk about RenderObject itself, you need to understand something called Flutter's three-tree architecture. When you write Flutter code, you're actually working with three separate trees that all work together. The first tree is the widget tree. This is what you write, your code. Widgets are just configuration objects. They're blueprints. They describe what you want. A container widget says, I want a box with this color and this size. That's it. Widgets are immutable and cheap to create. The second tree is the element tree. This is Flutter's internal manager. For every widget you write, Flutter creates an element. The element is what actually owns the state, and it links the widget to the render tree. Think of it as the glue layer. The third tree, and this is our focus today, is the render tree. This is where the actual work happens. Every node in the render tree is a render object. The render tree handles layout, painting, and hit testing. So every time you write a widget, under the hood, Flutter eventually creates or reuses a render object for it. The render object is the real worker. The widget is just the instruction manual. So what exactly is a render object? RenderObject is an abstract base class in Flutter's rendering engine. It lives in the Dart UI and Flutter rendering packages. It is the foundation of the entire render tree. Every visual element you see in a Flutter app, every box, every text, every image, every button, is ultimately handled by some class that extends RenderObject. Now, RenderObject itself is abstract, meaning you can't use it directly. But it defines a contract, a set of responsibilities that every render object must fulfill. And those responsibilities are exactly three. 1. Layout. The render object figures out, how big am I? Where am I positioned? It does this by receiving constraints from its parent and calculating its own size. 2. Painting. Once it knows its size and position, the render object draws itself on a canvas. It calls paint methods to put pixels on the screen. 3. Hit testing. When you touch the screen, Flutter needs to know which render object was touched. This is called hit testing. Each render object can declare whether a given point is inside it or not. These three responsibilities, layout, paint, hit test, are the entire job of a render object. Let's go deep on layout first, because this is where Flutter's genius really shows. Flutter uses a layout protocol with a very simple but powerful rule. Constraints go down, sizes go up, parent sets position. Let me explain this with an example. Imagine you have a parent widget, and inside it a child widget. The parent tells the child, you must be at least 100 pixels wide and at most 300 pixels wide. These are called constraints. They flow downward from parent to child. The child looks at those constraints, does its own calculations, and says, okay, I'll be 200 pixels wide. The child sends its size back up to the parent. Now the parent knows how big the child is. The parent then decides where to position the child. That's the parent's job alone. In code, this layout process happens inside a method called performLayout. Every render object that does layout must override performLayout. Inside this method, you receive the constraints, calculate your size, and if you have children, you call layout on each child too. Here's what that looks like at a basic level. In the performLayout function, the first thing we do is tell the child to lay itself out, passing along the constraints we received, and setting parent uses size to true so we can use the child's size afterward. Then we set our own size to the biggest size allowed by the constraints. The constraints here, for the most common case, is a box constraints object. It has four properties: min width, max min height, max height. The child must fit within these. This single, elegant protocol is why Flutter layouts are so fast and predictable. No layout cycles, no ambiguity. Let me show you a slightly more real example of performLayout so you can really feel what's happening. Imagine you're creating a custom render object that wraps a single child and gives it some fixed padding. In performLayout, you'd first tighten the constraints by subtracting the padding. Then lay out the child with those tighter constraints. Then set your own size as the child's size plus the padding. Here's the code. Here, we start by defining a padding value of 16 pixels. Next, we shrink the incoming constraints by that padding on all sides to get the constraints we'll actually give to our child. Then, we lay out the child using those smaller constraints, again allowing ourselves to use its size afterward. Finally, we set our own size by taking the child's size and adding the padding back on both sides, for both the width and the height. See what's happening here? You're being the responsible parent. You shrink the available space by your padding, let the child decide how big it wants to be inside that space, and then declare your own final size based on that. This is the layout dance that every container-like widget performs.
Now let's talk about the second responsibility, painting.
After layout is done, Flutter knows the size and position of every render object. Now it's time to actually draw them. Painting happens in a method called paint. It receives two arguments, a painting context and an offset. The painting context gives you access to a canvas. This is the actual drawing surface. It's the same canvas API you might have seen in Flutter's custom painting. The offset tells you where to start drawing, the top left position of your render object in the coordinate space. Here's what a basic paint method looks like. In the paint function, we first create a blue paint object that we'll use for drawing. Then we draw a rectangle on the canvas. The position and size come directly from the offset and size of this render object. After that, we check if we have a child, and if we do, we paint it on top, passing along the same offset so it lines up correctly. Notice a very important detail. You paint yourself first, then you ask the context to paint your child. This is how Flutter builds up the visual layer from back to front. Parents draw first, children draw on top. Also notice offset and size. This is a Dart shorthand that creates a rect from an offset and a size. It's Flutter shorthand that says, create a rectangle starting at this offset with this size. The third responsibility is hit testing. When you tap on the screen, Flutter doesn't magically know which widget you touched. It has to figure it out by walking down the render tree and asking each render object, did the tap land inside you? This is done through the hitTest method. For RenderBox, the method looks like this. Here's what this hitTest function is doing. First, Flutter receives a tap position. Then the RenderBox asks, is this tap inside my size? If the tap is outside, the answer is immediately no, and the function returns false. But if the tap is inside, Flutter continues checking. First, it asks the children, did any child get tapped? If one of the children says yes, then this render object is part of the hitTest path. If no child handles it, the render object asks itself, do I want to handle this tap? That's what hitTest self is for. If either the child or the object itself claims the hit, Flutter adds this render object into the hitTest result, along with the tap position, and returns true. Otherwise, it returns false. So the whole idea is simple. Check the bounds, ask the children first, ask yourself second, and if anyone accepts the tap, register the hit. Here's the logic. First, check if the tap position is inside our bounds. If yes, check if any child wants to handle it. If no child claims it, check if we ourselves want it with hitTest self. If anything claims the hit, we register it in the result and return true. This cascades through the entire tree until Flutter finds the deepest render object that handles the touch. And that's what triggers your gesture detector or inkwell. Now let's talk about two incredibly important methods, markNeedsLayout and markNeedsPaint. Flutter doesn't relay out or repaint the entire screen every frame. That would be incredibly wasteful. Instead, it uses a dirty flag system. When something changes, say a widget's size might change, you call markNeedsLayout. This flags your render object as dirty, meaning it needs to be relayed out. Flutter then schedules a layout pass for the next frame, but only for the parts of the tree that are dirty. Similarly, when only the visual appearance changes, but not the size or structure, like a color change, you call markNeedsPaint. This tells Flutter, I need to be repainted, but my layout is still valid. Why does this matter? Because it's the secret to Flutter's performance. If you change a color deep inside your widget tree, Flutter doesn't relay out the entire page. It just marks that one render object as needing a repaint and only repaints the affected area. In a custom render object, you'll typically use these when a property setter changes. Here we have two setters that show a very important concept. For the color setter, if the new value is the same as the current one, we just return early and do nothing. But if it changed, we update it and call markNeedsPaint. This tells Flutter to only repaint this widget without going through layout again. For the padding setter, same idea, we skip if nothing changed. But this time we call markNeedsLayout because changing the padding can affect the size, so Flutter needs to redo the layout as well. This distinction is really important for performance. Only trigger what actually needs to happen. This is the clean, efficient pattern every Flutter render object follows.
Now let's talk about the most important subclass of RenderObject, RenderBox. RenderObject itself is very generic. It doesn't know anything about 2D boxes, widths, or heights. It only knows about an abstract concept of layout and paint. RenderBox extends RenderObject and adds the concept of a 2D Cartesian coordinate system. This is the system 99% of Flutter widgets use. With RenderBox, positions are expressed as offset x, y. Sizes are expressed as size width, height. Constraints become box constraints with min, max width, and height. Almost every widget you use, container, text, padding, row, column, stack, is backed by a RenderBox subclass. The hierarchy looks like this: RenderObject, RenderBox, RenderParagraph, Text Widget, RenderImage, Image Widget, RenderFlex, Row and Column, RenderStack, Stack Widget, RenderDecorated Box, Container Widget. There's also RenderSliver for scrollable areas, but that's a topic for another video. For now, just remember, when you create a custom render object, you'll almost always extend RenderBox, not RenderObject directly. Okay, now let's put everything together. Let's build a real, custom render object from scratch. We're going to create a simple colored box with a configurable color and a fixed size, essentially recreating a tiny version of what Colored Box does internally. Here's the full code. Here we have a complete example, a render object called RenderColoredBox. In the constructor, we take a required color and store it in a private field. We also expose a getter and a setter for that color. The setter has a small but important optimization. If the new color is the same as the current one, we do nothing. Otherwise, we update it and call markNeedsPaint, because only the visuals changed, not the size. In performLayout, we simply take up as much space as the parent allows. Nothing fancy here. And in the paint function, we draw a filled rectangle using the offset and size, colored with whatever color is currently set. Let's walk through this line by line. First, we extend RenderBox, not RenderObject, because we want the 2D system. We store _color field privately and expose it through a getter and setter. In the setter, we call markNeedsPaint when the color changes, because changing color only requires repainting, not relayout. In perform-layout, we simply take up as much space as the parent gives us. Constraints.biggest returns a size with the maximum allowed width and height. In Paint, we draw a filled rectangle using drawRect. The offset and size shorthand gives us our bounding rectangle. We pass a paint object set to our color. That's a fully functional render object. Clean, efficient, complete. So why does Flutter even have this system? Why not just let widgets paint directly?
The answer is separation of concerns and performance. Widgets are designed to be simple and cheap. You can create thousands of widgets per frame. They're just configuration objects. They don't do any heavy lifting. The heavy lifting, layout math, canvas drawing, event handling, that's what the RenderObject layer handles. And because it's separate, Flutter can be extremely smart about when to redo work. When a widget rebuilds, because of a set state call, Flutter compares the old and new widget and decides whether to update the existing render object or create a new one. In most cases, it just updates the properties of the existing render object without creating a new one. This is hugely efficient. RenderObject also gives you maximum control.
If you're building a game engine, a custom layout, or a highly optimized chart, you can bypass the widget layer entirely and work directly with render objects for maximum performance. RenderObject is Flutter's rendering bedrock. Everything above it is built for developer convenience. But when you need raw power, RenderObject is where you go.
Let's recap everything we covered today. Flutter has 3 trees: widget, element, and render. The render tree is made of render objects. A render object has 3 jobs: layout, paint, and hit testing. Layout follows the rule: constraints go down, sizes go up, parent sets position. The performLayout method is where size is calculated. The paint method is where drawing happens on the canvas. hitTest determines if a touch point lands inside you. markNeedsLayout and markNeedsPaint make Flutter's rendering efficient by only updating what actually changed. And RenderBox is the concrete subclass you'll use for 99% of custom rendering in 2D space. RenderObject is one of those topics that once you understand it, the entire Flutter framework just clicks. You stop being confused by constraints. You understand why layouts work the way they do. You understand how custom painters relate to the widget system. If you found this valuable, subscribe, because we're going to be diving deep into Flutter's internals, one concept at a time. See you in the next one.